Check it out now, y'all.
nanoHUB-U, online instruction.
Hi, and welcome back. This is the start of the third week of the course called Fundamentals of Atomic Force Microscopy. And in this week of the class, we're going to start to discuss in detail some of the experimental aspects of atomic force microscopy. But before we begin that discussion, we want to finish up with these tip sample interactions, and in particular, we want to discuss the water meniscus that forms between the tip and the substrate, and we want to discuss what new effects this meniscus will bring about in the practice of atomic force microscopy. I'd also like to say that the online forum is going well. We're getting some very nice comments and some nice discussions back and forth between you and me. So please keep your questions coming and use that venue to sort out issues that perhaps aren't made very clear in the course of the lectures. In terms of a week 3 overview, we're going to start to branch out and do a variety of different topics. The big picture view of this week of lectures is given in this particular slide. And we're going to focus an awful lot on the instrumentation, which is in the upper right corner of the view graph. We're going to start to talk about approaching the tip to the substrate and measuring forces. So these are topics that we're going to cover this coming week. But before we begin that, let's focus a little bit on the water meniscus that forms between the tip and the substrate. This is an important effect, especially if you're doing experiments under ambient conditions. And basically, we have to start with a pretty high-level discussion of the water vapor or a liquid vapor interface. I tried to schematically indicate that interface in this slide. The dominant feature that you have to be aware of is that there's about a 1,500 reduction in the molecule number per unit volume between the vapor and the liquid phase. So in the vapor, there's something on the order of 2 times 10 to the 19th molecules per cubic centimeter. In the liquid phase, the number of molecules is increased by something on the order of 1,500. This just simply means that molecules at that liquid vapor interface experience a rather large and significant asymmetry in the way they interact one with respect to another. And this asymmetry gives rise to a curvature of the liquid vapor interface. And this curvature can be characterized by a radius of curvature r, as I've indicated in the right-hand diagram here. So a discussion of water meniscus effects in AFM ultimately comes back to mapping out the curvature of the liquid surface that forms between the tip and the substrate. For those of you that may not know, the curvature of a liquid surface has rather far-reaching and important consequences. So in this particular lecture, there are more than one appendix that I've attached to the lecture to discuss these various issues in a little bit more detail than I can go into during the course of the lecture. And so I refer you to the first appendix for a very general discussion on how to quantify the curvature of a surface. And the way this is done is by using something called the radius of curvature. In particular, it's the radius of curvature at a point on the surface. And what you can show is that if you measure the radii of curvature in 2 planes perpendicular to one another at a particular point, those 2 numbers can be used to completely characterize the curvature of the surface at that point. And so therefore these 2 numbers, R1 and R2, are going to play a prominent role in the discussion that follows. There are 2 important results that we'd like you to know about in order to understand this water meniscus that forms between the tip and the substrate. The first result is referred to as the Laplace equation, and the Laplace equation basically says that if a liquid-vapor interface has a curvature associated with it, there has to be a pressure difference across that interface. So the equation that governs that pressure difference is given on the bottom of the slide. The derivation of this equation is given in the appendix of the lecture, so you can follow through with that on your own. But the basic point is that if you have a liquid surface, if the liquid surface has a flat interface between the vapor and the liquid, that implies that the pressure inside the liquid is equal to the pressure outside the liquid. If the pressure inside the liquid is greater than the pressure outside the liquid, then the liquid vapor interface acquires a curvature, as I've shown in the middle diagram. And if the pressure of the liquid inside, if the pressure of the liquid is less than the pressure of the vapor, right? Then the liquid vapor interface will acquire a concave curvature, as shown in the third diagram in this slide. So this is an important result. It's very simple. Just by observing the curvature of the surface, you can tell whether the pressure inside the liquid is greater or less than the pressure of the vapor surrounding it. This young Laplace result, which goes back to the early 1800s, has pretty far-reaching consequences. And here I just show that if you calculate the pressure difference across, let's say, a drop of water with a radius of 1 micron, what you find is that the vapor pressure inside is 1.5 atmospheres, the pressure outside is about 1 atmosphere. So there's about a factor of 1.5 atmospheres difference in the pressure just due to the curvature of the liquid drop. The second result that maybe is not so obvious is that if the surface of a liquid is curved, then the equilibrium vapor pressure of the liquid must change. It can't be the same as it is for a flat liquid surface. And this fundamental result is described by something called the Kelvin equation. Again, I provide a derivation of the Kelvin equation in the appendix. There are many ways to derive this equation. Some are very general. I picked a very particular one so you can see how the derivation evolves. But the fundamental result is that the ratio of the vapor pressure above a curved surface to the vapor pressure above a flat surface can be described in terms of this equation that's displayed on this slide. The two important parameters that describe the ratio of this vapor pressure, actually it's the natural log of this ratio of vapor pressures. The two important parameters are the radii of curvatures R1 and R2 of the liquid vapor interface. And in addition to that, you have to know the temperature T in degrees Kelvin of the interface. You need to know the universal gas constant, and you also need to know the molecular or the mole volume of the liquid involved. So I give numbers for those quantities on this slide. The Kelvin equation is very useful for understanding curved interfaces and the rate at which these curved interfaces, for instance, evaporate. So if you have, let's say, a drop of liquid on a flat surface, or if you have small pores in a solid, liquid will condense into those pores at an accelerated rate due to the Kelvin equation. Kelvin equation is also used to describe bubbles in liquids. So these are a few of the applications of this equation that you'll find in the literature. Now for our purposes, it's important to follow through on these two equations, and I try to show that in this slide. First thing you have to realize is that any experiment that's done in ambient conditions, all the surfaces are basically coated with a very thin layer of water. This is just a result of the kinetics of molecules striking the surface, and the details of that calculation how to estimate how quickly that water layer forms, that's also covered in one of the appendices of this lecture. So both the tip, which is represented as a sphere in this diagram, and the substrate, which is represented as a flat plane, both those objects are coated with this thin layer of water, thickness we'll just call small h. When the tip comes into contact with the surface, a water meniscus neck forms. This water meniscus neck is characterized by two radii of curvature, as I show in this particular diagram. And under equilibrium conditions, these radii of curvatures R1 and R2 have to be determined by the Kelvin equation, which relates the relative humidity of the air to the two radii of curvature R1 and R2. Now, when you use the Kelvin equation, you have to be aware of the fact that there are sign conventions for the radii R1 and R2. And so for the particular application that we've got in mind here, the radius R1 tends to be described by a negative number. The radius R2 is described by a positive number. And these sign conventions have to be followed if you use the Kelvin equation. How thick is this water layer that forms? Well, there are some measurements in the literature that you can find. I just reproduce a graph here, and I just mentioned that at 30% relative humidity, which is relative humidity typical in most climate-controlled buildings in the United States, right? For 30% relative humidity, you've got something on the order of a water layer of about 0.8 nanometers that forms. Now, the exact value depends on a lot of facts, a lot of conditions, whether the surface is hydrophobic, hydrophilic, what the surface is made of. But we can use this number, 0.8 nanometers, as a rough estimate for the thickness of the water layer on both the tip and the substrate if you're doing experiments in a reasonably modern facility. How quickly does this water layer form? Well, again, that's discussed in the appendix. It's very, very fast, microseconds of time. So if you have a substrate or a tip that's in, let's say, a vacuum and you expose it to air, certainly in a second or so, the whole surface would be covered with a water layer. So you can't avoid it. It's always there. At contact, when the tip comes into contact with the substrate, it's a fair question to ask what determines these two radii of curvatures, R1 and R2. And the answer is the Kelvin equation has to be used in order to estimate those radii of curvature. So I just worked through some of the numbers here. It turns out the scale of the effect is set by this ratio that's shown by blue on this slide. It's the molar volume divided by the universal gas constant times the temperature T in degrees Kelvin, all multiplied by the surface energy of water, gamma. And if you work through those numbers, you'll find that the characteristic length scale for water is something on the order of half a nanometer. So this sets the scale for the discussion that we're going to follow. That's going to follow. In particular, we could ask the question, how big is R1, how big is R2, let's say at 30% relative humidity. I run through that calculation in this particular slide. When I did this calculation, I assumed that R1 was much, much smaller than R2, so I neglected R2 in the calculation. And you can see that the curvature of that water meniscus ranges from a very small number at 0% relative humidity. It starts to approach 10 nanometers as the relative humidity gets high. And at a 30% relative humidity, which is sort of our benchmark number, we find that the radius R1 is on the order of a half a nanometer. So it's comparable to the thickness of the water layer itself. This is just a back of the envelope calculation to give you a sense or a feel for these numbers. Students often think that the water that forms, this water meniscus that forms between the tip and the substrate, they say, well, geez, it's so small, it's going to evaporate very rapidly. That's not the case. In fact, the Kelvin equation tells you that water vapor will condense into that tiny region between the tip and the substrate, and water will continue to condense until the radii R1 and R2 match that given by the Kelvin equation. So in equilibrium, that water layer is always there, that meniscus layer is always there. It's very hard to get rid of it. The only way to get rid of it is to reduce the humidity in your AFM down to close to arid conditions, 0% relative humidity. Now, it follows that since this vapor, this water meniscus has a radius of curvature, that radius of curvature implies that there's a pressure difference inside the liquid versus outside the liquid. And that pressure difference implies that there's going to be a force that's exerted on the tip just due to the presence of that water meniscus between the tip and the substrate. And that meniscus is going to produce a capillary force which actually binds the sphere to the flat plane. It binds the tip to the flat plane. And it's kind of interesting to try to estimate how big that capillary force might be, because simply if you try to lift the tip from the substrate, you're going to have to apply a force to the tip that's great enough to overcome that capillary force. So it's useful to be able to estimate how big that capillary force might be. So to do that, you got to know the Laplace pressure, which is given by the first equation in this slide. And that Laplace pressure is related to the relative humidity through that term that contains the natural log. This pressure difference between the liquid and the vapor, right, acts over a surface area A, which is indicated by which is approximated in this discussion by a circle of radius r sub cap. And so to calculate the capillary force, you have to multiply the pressure, the Laplace pressure, by the relevant area. And I show that in the last equation here, right? The relative humidity is specified by the ratio of the natural logs of the pressures of the vapor over a curved surface compared to the vapor pressure over a flat surface. So that enters into the calculation. And the thing that you have to recognize is that this radius r cap will depend on all the parameters in the problem. It'll depend on the thickness of the water layer H. It'll depend on the radius of the tip. It'll also depend on these radii of curvature R1 and R2 that characterize the liquid that's trapped between the tip and the substrate. So in the next slide, I just try to estimate the magnitude of this capillary force. Again, there's a geometric discussion in Appendix 4 that you have to work through that allows you to estimate in a reasonably straightforward way this parameter r sub cap that appears on the first equation here. And what I show in that appendix is that this radius r sub cap can be estimated in terms of the square of the quantity 2 times the square root of the tip radius times the thickness h of the water layer plus the radius of curvature R1, the smallest radius of curvature that characterizes this liquid meniscus layer. If you factor out terms in that equation, you can end up with the third equation on the slide, which says that the capillary force is going to be equal to 4 pi times the surface energy of water, gamma, times the radius of the tip, times this geometric factor, which I actually evaluate. So I use the numbers that we've already estimated. I pick 30% relative humidity. So H plus R1 is going to be a number on the order of 1.3 nanometers. The prefactor here that contains the universal gas constant and the temperature T, right? We've already estimated that at room temperature. That's on the order of 0.5 nanometer. And if you pick relative humidity of 30%, the natural log of the vapor pressures gives you a number on the order of 1.2. So as you can see, when you multiply all that out, you would expect that the presence of this water meniscus increases the adhesive force given by 4 pi gamma r tip by something on the order of a factor of 3. So not surprisingly, there have been measurements made of this quantity. I show some representative data here. This data is taken, measures the adhesive force in nanonewtons as a function of the relative humidity. You can go to 0% relative humidity to get an estimate of 4 pi gamma r tip for this particular case. And then if you go to the 30% relative humidity, you find that the adhesive force that was measured experimentally is about 2.5 times to 3 times greater than the adhesive force that results when the measurement is made in 0% relative humidity. And of course, this number that we estimate just above is a factor of order 3, which agrees qualitatively with the experimental measurements of liftoff force due to the water meniscus. So the bottom line is, anytime you do AFM measurements in ambient conditions, the tip will experience a greater liftoff force by something on the order of a factor of 2 or 3, right? Compared to what you might measure if the measurements were done in 0% relative humidity. Of course, if you compare this to the results that we've already discussed in prior lectures, right? I've got the adhesive force due to Deryagan approximation. I've also got the adhesive force due to the JKR approximation. These are numbers, and these numbers are independent of relative humidity. They clearly do not match the trends that the experimental data shows. So if you look at the data, it's interesting, right? The liftoff or the adhesive force that the tip experiences, that adhesive force actually drops as the relative humidity increases, and that drop-off can be attributed to just the way the natural logarithm of the ratio of the vapor pressures above a curved surface and a flat surface, that gives you the drop-off that you see experimentally. So this simple model allows you to capture the fundamental aspects of additional adhesion due to the water meniscus. It gives you some insight into what that additional adhesive force is all about. And it just means that when you do experiments, there's going to be an additional liftoff force that you're going to have to supply to remove the tip from the substrate. That additional force is referred to as the capillary force. And there are various models in the literature. Some are very simple. The one I discussed here is pretty straightforward. There are models that are a lot more complex, but you're going to have to take this capillary force into account if you're going to try to understand experimentally the adhesive forces that you measure, if those measurements are done under ambient conditions. So that's all I wanted to say about the meniscus force. There's a lot of material in the appendix for those of you that want more of the details. So I encourage you to sort through that on your own time. And I'll end this lecture by just saying that when we come back, what we're going to do is provide a brief overview of VEDA. This is this atomic force simulation software that's been developed by Arvind Raman and his group here at Purdue University. We're going to start to walk through how to use this software and try to provide some information for you to make sure that you understand how the software works. This is going to be important as the lectures move through into the 4th and 5th week of part 1. So thanks for your comment, and we'll see you at lecture 2.